In today's digital battlefield, toxic symbols hide in plain sight, fooling even top multimodal models. Today, discover how infusing clip with human knowledge turns detection accuracy from guesswork to precision strikes. Good day, everyone. I am Paula Mendoza from the Technological Institute of the Philippines, and today I am pleased to present my research titled Comparative Assessment of Knowledge Augmented Clip and Modern Models on Toxic Language Detection Metrics. Unimodal text-based toxic language detection models struggle with inherent biases from training data, which lead to unfair or inaccurate classification results. Multimodal toxic language detection faces the challenge that harmful messages usually arise from the interaction of multiple modalities. Traditional unimodal methods miss subtle toxicity conveyed through these combined contexts. There is a scarcity of comprehensive evaluations comparing knowledge-augmented vision language models like Knowledge Clip to establish unimodal and multimodal baselines, limiting understanding of these models through potential and robustness. This research addresses these challenges through systematic comparative evaluation and knowledge augmentation in multimodal toxic language detection frameworks. This study presents a comprehensive evaluation of knowledge-augmented CLIP framework for toxic content detection, demonstrating its superiority over unimodal and other multimodal models across key metrics such as accuracy, precision, recall, F1 score, and robustness. Evaluating the knowledge-augmented CLIP framework by comparing it to the unimodal and multimodal models is important because it helps us understand how well this new approach performs in terms of key detection metrics. It also shows how robust and reliable the framework is when faced with different and challenging detection tasks. This kind of comparison is essential to highlight the real benefits of adding knowledge augmentation to multimodal detection, guiding future research and practical use in identifying toxic content more effectively. Based on the related literatures, unimodal image models like ResNet 50 excel in visual feature extraction for hateful imagery via residual connections, outperforming other CNNs on datasets such as Mute, yet struggle with ambiguity absent textual context. On the other hand, vision transformers or VIT leverage self-attention for broader image context, showing promise in hate detection despite limited unimodal applications, often adopted from multimodal successes. And we also have the text-based for such as BERT and Roberta, which capture nuances, hate speech through bidirectional encoding and fine-tuning, with Roberta leading in accuracy and F1 scores, though challenged by dataset imbalance and biases. Visual BERT. For multimodal models in hateful content detection, we have Visual BERT, which integrates image region features with text embeddings in a single transformer framework, effectively capturing visual textual interactions for detecting hateful memes and posts reliant on both modalities. LXMERT, on the other hand, employs separate encoders and cross-attention layers for explicit vision language modeling, capturing fine-grained object-text relationships, which are essential for nuanced hate speech in memes and image caption pairs. Lastly, we have CLIP, which learns aligned image-text representations for zero-shot hateful meme detection, enhanced by hybrid models and contrastive learning for resilience. though challenged by training biases and dataset scarcity. So before training the model, these research utilized a range of datasets which focused on hate symbols, toxic content, and cultural context to train and evaluate the models. The primary resource was the hate symbols database, which are publicly accessible and comprehensive collection of images paired with contextual descriptions of hate symbols, which are linked to hate crimes, extremist ideologies. Recognizing the scarcity of paired text-image datasets, a custom hate symbols dataset was manually created, providing both visual examples and detailed explanations. Additional multimodal datasets included the Facebook meme dataset and MMH S150K, though their text was primarily OCR extracted rather than descriptive captions, posing challenges for training. For non-hate examples, 3 public datasets were employed. The Flickr 30K dataset with multiple descriptive captions per image, the popular brand logos image dataset where descriptive captions were generated from file names using templated phrases, and the geometric shapes dataset, similarly captioned and balanced through random sampling. These datasets collectively enabled robust, multimodal knowledge integration for toxic content classification. Presenting here are the samples from our datasets. We have figure 1, which is the sample screenshot of the content from Flickr 30K with 5 descriptive captions stored in a list. Figure 2, on the other hand, is the sample screenshot of a newly created CSV, which chosen caption of Flickr 30K. So for each image and in Flickr 30K contains 5 descriptive captions stored in a list. So to prepare the data, a custom pre-processing script was implemented to iterate through the list of captions and select one that do not exceed from CLIP's 77 token limit. For figure 3, we have here a sample screenshot of the popular brand logos image dataset with created descriptive captions. Since this dataset does not include descriptive captions, the researchers generated their own by utilizing the image file names, combining them with predefined phrases such as the following examples here. In this study, the researchers implemented the use of descriptive captions as the knowledge augmentation approach rather than the structured knowledge graphs. So each image in the dataset was paired with carefully written caption that explicitly encodes human knowledge about whether the content represents a hate symbol or a non-hate context. So for hate symbols, the captions provided not only the visual description of the elements present in the image, but also their historical or cultural associations with hate ideologies. For non-hate examples, the captions describe the objects in a straightforward manner, ensuring there was no misleading interpretation. By creating this dataset, the captions served as a semantic knowledge layer for CLIP, allowing the model to learn both the visual appearance and the contextual meaning of the symbols. This caption-based strategy provides a form of knowledge augmentation that directly integrates human expertise into the training data without the need for building complex knowledge graphs. The training and fine-tuning of all the models in this study went through with the same learning rate, batch size, and number of epochs. In this figure 4 here shows the training and validation loss curves over 20 epochs. Both losses consistently decrease as training progresses, indicating that the fine-tuned VIT model is effectively learning from the dataset. By around epoch 15 to 20, the loss values stabilize and become very small, suggesting that the model has converged successfully. On the other hand, figure 5 here illustrates the training and validation loss curves across 20 epochs. The training loss decreases consistently, reflecting that the fine-tuned ResNet 50 model is effectively fitting the training data. This trend is reinforced by the steady increase in training accuracy, which reaches by 0.95 at 20 epoch. Figure 6 here shows the training and validation loss curves for the fine-tuned BERT model over 5 epochs. So both curves drop rapidly and stabilize at extremely low values by epoch 5, indicating that the model converged very quickly and effectively learned the tasks. While the figure number 7 illustrates that the training and the validation loss curves of the fine-tuned Roberta model across epochs both losses decreases extremely rapidly, reaching and stabilizing at 0.0 by epoch 4, which indicates that the model quickly learned the task and generalized perfectly to the validation set. For the multimodal results, in figure 8 here, this illustrates that the training and the validation loss curves over 20 epochs, both losses decreases consistently, with the most rapid improvement occurring within the first 10 epochs. The validation loss drops from 0.34 at the start to 0.06 by epoch 20, which indicates that the model effectively generalizes the unseen data and has successfully converged. Figure 9 here shows the training and validation loss trends of the training progress for LXMERT across 20 epochs. Both curves demonstrate a significant and consistent decrease, with the validation loss dropping from 0.48 in epoch 1 to 0.0093 by epoch 20. So this sharp early decline followed by a gradual tapering indicates that the model is effectively learning and steadily approaching convergence while maintaining strong generalization to unseen data. The results presented here in this table shows that the other multimodal models, such as the Visual BERT, LXMERT, also benefit significantly from fine-tuning. Baseline versions show low accuracy and precision but high recall, indicating many false positives, whereas fine-tuned models will achieve high overall performance, with LXMERT fine-tuned reaching 99% accuracy. And furthermore, the data shows also that while multimodal clip baseline models have inconsistent and often poor performance, their results are greatly enhanced by fusion-based approaches. Early fusion emerged as the most effective strategy among all fusion methods, achieving the highest performance with 97.26% accuracy and 97.25% F1 score. As a conclusion, the results highlight that the knowledge augmented CLEAP framework delivers superior performance compared to both unimodal and other multimodal models in terms of detection, accuracy, precision, recall, and F1 score and robustness. While baseline models generally struggle with low or inconsistent results, the integration of knowledge augmentation within the CLEAP framework markedly elevates detection capabilities. This indicates that incorporating external knowledge into the CLIP architecture strengthens the model's ability to accurately detect toxic content by improving its understanding and representation of multimodal data. Again, the knowledge augmented CLIP framework offers a more effective and robust solution for toxic language classification than existing unimodal and multimodal models, which lack such augmentation. And that concludes my presentation. Thank you very much for listening.